Hello everyone, my name is Isra Shaheen and today I will present my review of paper titled UAVBS Integration with Urban Infrastructure. This presentation is part of Wireless Communication course of Master Degree at the Islamic University of Gaza and was supervised by Dr. Ammar Abu Hadrous. The topic here focuses on how unmanned or uncrewed aerial vehicles can be used as base stations in urban environment, especially to improve energy efficiency and network coverage. Throughout this presentation, I will walk you through the motivation, deployment scenarios, technical challenges, and our proposed solution using a genetic algorithm for optimal placement. In recent years, UAVs or unmanned aerial vehicles have gained increasing attention as flying base stations known as UAVBSs. They are especially useful in 5G and 6G, sixth generation networks, providing on-demand wireless coverage, real-time data collection, and edge computing. UAVBSs are particularly helpful during temporary events, natural disasters, or in areas that are difficult to reach with regular ground infrastructure. So, however, there are some challenges. So the main ones are limited. Battery life, restricted payload, and airspace regulation. So our goal here is to find solution that balances energy efficiency and mobility while maintaining high quality wireless service. The paper we study suggests landing UAVs on urban infrastructure like lampposts or bus stops with charging stations to reduce energy use. So traditional cellular networks use over provisioning, which means having too much infrastructure even when demand is low. This causes energy waste and is not efficient during urban events like festivals. The demand for network capacity spikes temporarily. UAVs offer a flexible and cost-effective way to provide extra coverage exactly when and where it's needed. So in this slide, like what we see, there are two main deployment scenarios for UAVBSs. The first one is when UAVs are flying and moving according to user locations. And second scenario is when UAVs land on fixed urban landmarks like lampposts. Landing the UAVs can save a lot of energy since flying continuously consumes more battery power. Okay, this slide talk about the benefits. Integrating UAVBSs into urban environments brings several benefits. Okay, so the first one, it helps extend wireless service to areas that are undeserved or have poor coverage. Second one, UAVBSs support dynamic capacity, meaning they can respond to changing network demands during peak times or emergencies. Third one, they improve resilience and service continuity when ground infrastructure fails. And finally, they enable smart city applications and support IoT devices across the city. IoT, that's mean Internet of Things, and that's what we will talk about it in another slide here. Okay. So smart cities and IoT use cases. Here, in smart cities, UAVBSs can support many practical use cases. For example, they can help with traffic monitoring, emergency communications, and public safety during disasters. They also support environmental sensors and can provide temporary internet coverage during events like concerts or sport games. Okay, here in this slide we'll talk about the cost. Using UAVBSs also helps reduce the cost of building permanent infrastructure instead of installing many base stations everywhere. UAVs can be deployed only when needed. This avoids investing the expensive ground equipment that may not always be used. Also, UAVs can be reused in different cities or events, which increases their value and efficiency. So, however, there are some challenges to consider when integrating UAVs with urban infrastructure. Legal and airspace regulations vary by country and can limit where UAVs can fly or land. Also, UAV battery life is limited, so they cannot stay in the air for long time. Also, security is another concern. UAVs needed strong cybersecurity protections to prevent hacking or misuse. Okay, so in this slide, we'll talk about technical challenges. So there are challenges with signal interference. UAVs may interfere with regular ground-based stations, especially if they use the same frequency power, and spectrum management must be carefully planned. Also, weather conditions and the urban environment can also affect how reliable the UAVs are. Okay, so here proposed solutions, genetic algorithm, which they abstract with GA here. So to address this challenge, the paper proposes using a genetic algorithm to find the best places for UAVs to land. The algorithm chooses the optimal landing spots on urban infrastructure based on user certification, because is the most important here is the user certification and signal strength also. So this approach is scalable and energy efficient, making it suitable for large urban networks. Here, like what we see, there is figure 1. This figure explains the full concept of our UAVBS deployment strategy. The system starts with input data, like what we see here. Input data like user locations, urban infrastructure, and network performance. A genetic algorithm is used to find the best UAV landing spots, such as lampposts, monuments, bus terminals, or even park taxi also. So these landing spots include energy stations, helping UAVs recharge and save energy. The result is a system that improves energy efficiency while still maintaining high user certifications. So system modeling, urban setup. Okay, so in this slide, we show the city setup we used for simulation. We selected area, square, Brno, and added details like lampposts and bus stops. So these places are used by UAVs to land and charge. All the data is based on the actual maps, so the model is realistic and reliable. Okay, so in this slide, you can see that the user density and mobility modeling. So the simulation included about 5,000 users during a busy event like a festival. Two types of users were modeled: regular users and live streamers. The user movements were simulated using Manhattan and nomadic mobility models to reflect realistic urban behavior. So use the traffic models. Each user type has a different data pattern. Live streaming users were modeled using a gamma distribution, which reflects high and consistent data usage. Regular users the regular users were modeled using a long normal distribution, which represents a more typical variable usage. These traffic models help estimate how much network capacity is needed. So this slide shows the main parameters used in the simulation, like frequency. Frequency here is 3.5 gigahertz, the bandwidth 100 megahertz, and also number of UAVs between 6 and 12, coverage area 0.25 square kilometer, and the minimum user rate, which is 1.4 megabits per second. Here, these parameters reflect real-world 5G deployment conditions anyway. Okay, so in this slide, we can see here there is a figure. Okay, so here the simulation compared different deployment scenarios. It showed that landed UAVs used much less energy than flying ones. This confirms that placing UAVs on urban structures can help save battery also and reduce operational costs. That's what we see in this diagram. Another figure here. Here the graph in this slide compares user certification in different scenarios. Landing UAVs slightly reduced certifications compared to flying ones due to fixed locations. So, however, the energy savings are significant and user certification remains acceptable overall. In this slide, or from this study, we learn that landing UAVs on urban infrastructure greatly improves energy efficiency. Even if there is a small drop in user certification, it's fair trade-off for saving battery and cost also. So, optimizing where UAVs land can improve both energy and performance. Okay, so in the future, I will talk in this slide about the future. UAVs can work together with high altitude platforms or HAPS. Okay, so flying at a 20 kilometer altitude, this hybrid model combining UAVs and HAPS is a good step toward 6G networks. It can handle citywide coverage, emergencies, and high user demand with lower energy use. Okay, so in the conclusion, here I summarized everything that I discussed in my presentation. So, UAV BSs can use existing urban infrastructure to reduce energy consumption. Landing UAVs is more efficient than keeping them flying. There is a small trade-off in user experience, but it's worth it. The last one, the genetic algorithm provides a smart, flexible way to decide where UAVs should land. And here I can say thank you. Thank you for listening to my presentation. Also, if you have any questions,